thank you. Today I'll talk a little bit about broadband communication systems on a chip and how they're driving opportunities for analog and RF design. First, I'd like to review a little history, just looking at the history of your TV over the years. Back in the 50s, we started to see the first color TVs, these becoming more affordable around the 70s. And it wasn't until the early 2000s really that we saw flat panel TVs overtaking CRTs in terms of number of shipments. And of course today we have very high quality, affordable TVs throughout the home, large and always connected to the internet and all of the streaming content that you need. The key point here is that this evolution took over 60 years between where we started and where we are today. For comparison, let's look at your cell phone. Early prototypes in the 70s, shown here. I think the first commercial analog cellular device was in 79. Things really took off in the 90s with your 2G cell phones. A decade later, we had simultaneous voice and data with packet switching. And of course, today, your all IP network, smartphones, which you see everywhere with very high functionality and very high computing power. This evolution, by comparison, really mostly took place in the last 20 years or so. And today, you're getting this very capable cell phone with computing power that was only available on high-end PCs a few years ago, basically for free. And of course, today, you're seeing this technology everywhere. We have everything connected, TV available wherever you are. These are some ads from magazines around the world. On the left is Panasonic Blu-ray players and 3D TVs that, of course, as I mentioned, very affordable and you find throughout the home. And on the right are your 4G cell phones. And this enables you to take your TV with you wherever you go. And again, you get this at a very, very low price. So over the past 10 or 15 years, this digital revolution has really dramatically changed how people around the world are communicating, interacting. And this is due to a couple factors. Of course, the proliferation of the internet, which is available everywhere now, and also the affordability of the devices available to the consumer. So these factors, the growth in users, as well as the increased amount of data and the format of the data from voice to data to high-definition video is resulting in this insatiable demand for bandwidth. And broadband communication systems on a chip are the foundation that's enabling this revolution. Nanometer digital CMOS technologies are the key factor here in enabling system-on-a-chip designs. And these are provided through cost-effective processes with high performance and also meeting low power requirements. In this presentation, I'll give a little overview of broadband communications SoCs over the last 10 years or so. As we'll see, through advanced CMOS technology, we're able to integrate more and more into communication SoCs, but there are also additional processes required to provide the full system solution. Some of the examples we'll talk about are Power over Ethernet for network infrastructure, LNAs and PAs for tuners, and PMUs for the mobile space. And then I'll look a little bit at the future of SoCs and 20 nanometer technology and beyond, some of the challenges there and opportunities to continue to integrate more. 3D FETs and SOI is some of the process technology that's out there today, and there are some unique advantages as well as challenges. And I'll talk a little bit about 3D packaging. So what does the communication industry look like today? Basically, horizontal integration is a must. By horizontal integration, we mean the interoperability of all these different communication protocols. Starting with the cable network, the coax network in your home, connecting your TVs and gateways, including the Ethernet, which has your set-top boxes and your PCs, and then on to the Wi-Fi, Bluetooth, and other wireless networks combining all your handheld devices. So in order to be a player in this space, you need to have IPs across all these communication platforms in order to do the integration necessary. And this is a large opportunity for SoC companies. As I mentioned before, in addition to the number of users growing dramatically, there's a dramatic increase in the data needs of each user. Moving from regular phones to smartphones to tablets, we're seeing orders of magnitude increase in bandwidth requirements. And this is resulting in the explosion of the data bandwidth requirements in the mobile backhaul. Each of those communication protocols I mentioned are evolving dramatically. First here is the cellular network, and on the left here, the bandwidth requirements. Next we see the Wi-Fi increasing requirements. Bluetooth is shown here. Ethernet here, and cable as well, and DSL. Sorry to move a little too fast there. That was a cable. And here's the DSL requirements. So all of these communication protocols together are evolving very rapidly. And what we're seeing is the gap is decreasing between the consumer requirements and, the backhaul. So more work is needed in the backhaul to support all of this data traffic. I'd like to talk a little bit about the broadband market, just as an overview. There are three major segments of the communication market. Of course, Broadcom is active in all three of these. First is the infrastructure and networking. Next is the home broadband communications for all of your home connections. And then, of course, the handheld or mobile and wireless space. And each of these market segments is growing, which is enabling opportunities for wired and wireless convergence. The infrastructure market contains a few key areas from the service providers and the data centers onto the corporate enterprise network, and then onto the small business and home connectivity. In the home broadband, these applications are all centered around the applications in your home. The set-top boxes here, which are required for all of your cable and satellite connections for your TV. Broadband access solutions for your cable or cellular or DSL internet connection. And the consumer electronics, as I mentioned before, these connected TVs, Blu-ray players, and other video devices. And the third segment is the handheld or mobile and wireless segment. Here we have solutions for the mobile devices, that is the handheld phones and GPS devices, the wireless solutions for your home computing, for your laptop and your tablet, and also solutions for all of the consumer equipment to enhance your in-home experience. So as you can see, there are many pieces to this integration puzzle. And in order to play in this communication market and to integrate, you need to have IPs across all of these platforms. But we can't forget the need for software as well. In order to integrate in a single chip, you have to be able to offer the customer a single software solution. So integration is not just a chip issue. It's an IP issue, it's a hardware issue, and software. In the portable space, we've seen these, again, I'm jumping ahead. We've seen these independent devices for all these types of functions, from your cell phone to your cameras to your two-way radios and GPS. And we're rapidly seeing the movement toward integrating all these functions in a single device. And of course, what's that device going to look like? This is going to be your future smartphone. It's going to be always on, always connected to the internet, and at a very affordable price. So what are the technology trends that are enabling all of this integration? I'll talk a little bit about those. First of all is process technology. We're seeing a continued scaling of CMOS process technology every couple of years. And this is enabled by significant innovations in process technology manufacturing. In the 40 nanometer generation, we started to see the introduction of strained silicon, which is used to enhance the performance of the devices. 40 nanometers in high volume production today. In 32 and 28 nanometer generations, we saw the introduction of high K and metal gates to improve device performance. Now at 20 nanometer or 22 and below technologies, we're starting to see the integration of, or the introduction of 3D FETs. And I'll talk a little bit more about that later in the future trends. The message here is that we don't see any end to this scaling trend, at least for the next couple of generations. Certainly there are a number of challenges as we move to these advanced nodes. Cost is not a small one, but we expect there'll be innovations that can address those challenges. One thing that will come into play here is 450 millimeter wafers, which would offer additional cost benefits in this time frame. Another trend is the increase in compute power that we're seeing in even in the broadband products shown here. These are actually set-top box products from Broadcom. The compute power in the state-of-the-art set-top box is equivalent to a server-class CPU. And this is driven by the video requirements, all the video processing required in a new set-top box. So there's a lot of compute power in that cable box sitting underneath your TV. And this can only be done using advanced CMOS technology. We're also seeing an increase in the memory data rates, driving I/O count and speed. And again, these are broadband products, set-top box products from Broadcom. And we're seeing here 3 gigabit per second data rates in 28 nanometer, looking forward. The trend in analog is to integrate not only more functions, more analog functions in the die, but also to continue to increase the performance of those functions. So again, these are broadband communication products over the years, and you see more and more of the analog functions being integrated, as well as a higher functionality. And this can only be achieved in a cost-effective manner by relying on the advanced technologies. So here today, in 40 nanometer, we have all of these analog functions integrated in a single chip. One example of a 40 nanometer chip is shown here. This is a video decoder product. It includes 3D video, fast DVR, a DVR interface, HDMI, 1.3 gigahertz MIPS CPU. All these features integrated into one chip thanks to the availability of 40 nanometer CMOS. This chart shows the trend in video receiver clock frequency and bandwidth. Looking at the benchmark back in quarter micron 1990s time frame, 45 megahertz, that increased to 60 megahertz when 1080p was available. And we see that increasing rapidly as we scale to the newer technology, 6540 and now 28 with 3 gigahertz frequencies. And this is another example. This is a transmit function, an upstream DAC. What it shows us is that this 12-bit DAC at sampling speeds, sampling up to 2 gigasample per second is a reality thanks to the advanced CMOS technology. And the matching of these 4 channels is actually very good thanks to the inherent good matching in the 40 nanometer CMOS. Another key feature here is that no external PA is required. Those functions are performed using an LDMOS that is integrated in the standard CMOS flow. So to summarize, what are these enablers of the SoC resolution? Clearly, CMOS scaling is the big one. You get more for less, more performance, better power at lower cost. And this has also benefited analog significantly. In general, analog devices have gotten better through CMOS scaling. Noise performance has improved, matching gets better, power, gain bandwidth product All of these have improved, but we also need to employ good design engineering to resolve the issues with the power supply decreasing from node to node, which of course makes analog design very challenging. And what Broadcom employs is DSP-assisted analog design. And this is using the availability of those relatively inexpensive logic gates in the advanced process to make corrections for the imperfections in the analog. And as I mentioned before, it allows the development of a very broad IP portfolio, and the software that goes with it is equally important. However, not everything can be integrated in a standard mainstream CMOS process. There are limitations. There's a limitation in speed and noise performance. Power supply is too low for some applications. Oh, looks like we lost it. Power supply is too low for some applications. And you need additional non-CMOS or non-vanilla CMOS processes, or non-mainstream processes, to provide the complete SoC solution. I'll provide a few examples of these in the different market segments that we talked about. First is power over Ethernet, some front ends for broadband tuners, and then the PMUs. And these are all creating additional opportunities for analog and RF design. First of all, what's PoE? PoE is basically using the Ethernet cable to supply the power to your end device. The end devices are things like your voice over IP phone, your wireless LAN or Bluetooth access point, or maybe your security cameras. Older generations used what's called a mid-span hub to insert the power in between your Ethernet switch and your end device. However, newer configurations are end-span, where the PoE device is actually included with the internet switch. The power over Ethernet can be done in a couple different ways that it's illustrated here. One way is to use, to superimpose the power right on top of your data lines. The other is to use unused lines. In the case of Ethernet, you could use unused. Back up. Use the unused pairs here to provide your power. The key specifications here, that this is 48 volt DC and up to 15 watts of power. So the process requirements become very severe. Not the least of which is ESD, because now you have these long cables with this kind of voltage, so there's a lot of charge stored there. So ESD requirements are very challenging. Broadcom's solution is a simple and clean one where the high voltage device is integrated in one chip along with current sense circuitry, so this does not need to have external resistors for current sensing. But it places a lot of requirements on the process to do this kind of high voltage. The picture at the right here shows the Ethernet switch where a daughter card is inserted here that has the PoE device on it, and it's just right on top of the switch and the PHY located underneath. The second example I'd like to go through is tuners. And I'll talk just a little bit about the history of tuner integration at Broadcom. It wasn't too long ago that tuners looked like this typical CAN tuner, where all the devices on it were discrete devices, all had to be tuned and calibrated as part of the manufacturing process. And obviously that added with it a lot of extra time and cost. And we were able to integrate all these functions into one piece of CMOS silicon. And over the years, this has evolved into multiple channels. Here's an example of dual channel satellite tuner. Again, giving better performance, lower cost for the end application. Today, state of the art is full band, full band capture. And what full band capture means is that we can actually capture all of the channels from your satellite or other medium. And you can select any number of those channels using digital logic. So it's really the holy grail of radio design. You have one ADC on the antenna. Everything else is done in digital logic, providing the ultimate flexibility for your system designer. And this can only be done with relatively inexpensive advanced CMOS. But to go with all these tuner innovations, you need front ends to drive the RF and to go with all of those tuner solutions. This is an example of that. It's a front end module. And of course, you need low noise, you need high speed, you need to use something other than your mainstream CMOS process. In this case, 0.18 silicon germanium by CMOS is required. So the proliferation of those tuner technologies brings with it opportunities for specialty technologies, in this case, the front-end modules. The third example of these non-mainstream CMOS process is for PMUs. And PMUs, as the previous speaker mentioned, are required for a number of functions, especially in cell phone applications. These include audio and video, the displays, and the battery management. Broadcom's approach to PMU has been to integrate more functions in PMU die. These functions on the right are the ones that require the high voltage device. On the left, many of these are actually low voltage functions, but can be cost effectively integrated with the availability of 0.18 high voltage technology. And next, I'd like to talk a little bit about the future challenges and opportunities for broadband communication SoCs. So looking at 20 nanometer and beyond, there are a number of challenges for SoCs. Certainly cost is going to be a significant one as we move down into the newer technologies. Restricted design rules have become very restrictive. They're actually, for example, polysilicon can only be drawn in one direction. That puts a lot of constraints on the designer on his IP development. You may have to have multiple IPs for your IOs, for example, depending on which orientation they are. Lithography limitations are certainly being very challenging, and innovative technologies needed to overcome this. And the lack of voltage scaling is providing some challenge there because dynamic power is not reducing as fast as we'd like. Specific challenges for analog. Parasitics are becoming a real issue as we move down in technology. Transistor mismatch generally gets better, but it's very challenging as the device sizes get very small. And of course, those restrictive design rules have a big impact on your analog design. So a number of innovative technologies are offering new opportunities for SoCs and to address some of these problems. I'll talk about a few of these. First is 3D transistors, or FinFETs, fully depleted SOI, and also some innovative packaging solutions that may offer new opportunities for integration. First of all, FinFETs have been in the literature for a while. Intel made a recent announcement. They're introducing this in the 22 nanometer node. So it's been demonstrated and is actively being worked on by a number of suppliers. The basic concept of the FinFET, which is shown here on the right, is that the channel width is now extended in the vertical direction. That's the three-dimensional part of it. So you get that additional device width, and therefore you'll get additional performance. These pictures and these SEM micrographs were taken from the literature. And briefly, you can see there are different variations of FinFET, also called multi-gate FETs, where your gate might extend all the way around your device. Tri-gate FETs, which is the Intel variation, where you have the top surface is also a conducting surface. Another picture to illustrate the different variations of the FinFET is here, taken from the textbook, showing you can make FinFETs tall and skinny, or you can make them short and fat, or maybe even in cylindrical form. All are going to have different advantages and disadvantages in terms of processing cost and performance. Some of the key device advantages are shown here. Because of this very thin silicon film now, you have very good short channel control in the FinFET. And as I mentioned, you'll get higher drive currents due to that extra width, effective width that's provided. The threshold slope gets much better, providing reduced leakage and you'll get better area scaling of your device because now you're taking advantage of the third dimension. The challenges, certainly process complexity, which translate to cost, is a key challenge. And all of those additional steps require more manufacturing control. So this could potentially add cost as well. Width quantization is something that needs to be taken into account. That now you have your width of your device is essentially the height of that fin. So you have a fixed width that you have to use in all of your designs, and you'll have to adjust your methodologies for it. The EDA infrastructure needs to become mature, and there could be other challenges for analog in particular. Some of those capacitances may increase depending on what structure is used. Multi-threshold voltage support, which is a must for SoC design, will also be that much more challenging in this FinFET configuration. So while FinFETs are very promising, it's not clear yet that it's going to be the best process for SoCs or for analog. So a lot more work needs to be done to evaluate this. A competing technology at 20 nanometer and below is extremely thin or fully depleted SOI. For comparison, I've shown here the cross-section of a traditional bulk CMOS transistor. On the right is the FinFET we just talked about. The uniqueness of the SOI device is that you have a very thin silicon film on top of an oxide. And that gives you better device characteristics, as I'll show on the next slide. But the rule of thumb is that your silicon film needs to be about 1/4 of your gate length. So at a 20 nanometer gate length, that film thickness is already 5 nanometers. So clearly it's going to be very challenging to continue to scale that film thickness. Those advantages, one advantage is that this is a conventional planar CMOS process. So we're not using new FinFET type processing. The channel itself is very lightly doped, gives you that better subthreshold slope and better short channel control, similar to the FinFET, and also very good mismatch performance. The challenges are that there is some cost involved and that you require an SOI device as a starting SOI wafer as a starting substrate, and that has some cost with it. There are manufacturing challenges with the thin SOI. As I mentioned, the film itself needs to be deposited and controlled very uniformly, and then you need to be able to make connections to that film. So a lot of challenges go with it. Some design architecture needs to change because it's a little bit different than your bulk transistor. And your area scaling, while similar to bulk CMOS, is not going to offer you the same type of advantages or the same amount of scaling as you'll see in that FinFET. So finally, I'd like to talk about packaging technology, in particular through silicon vias. A couple of innovative technologies here offering new opportunities for integration. One is interposer TSV, and the other is the active silicon TSV. Now, interposers today are needed to meet the aggressive pad pitches that we see in the advanced CMOS chip, and then to fan it out into a lower cost package. But it also opens up opportunities for additional integration at the system level. Active silicon TSVs is the technology where the through silicon via is actually integrated along with the full CMOS process. And this could enable to use multiple die, optimize the process choices for each of those die, and then integrate them in a very cost-effective and high-performance manner. So first of all, interposers are shown here. In this case, the interposer is used as a fan-out to the tight ball pitch. In this case, a 65 nanometer ASIC is shown, and to integrate that with the lower-cost packaging. And this allows you to use low-cost packaging with the advanced technologies and not have to go to more exotic packaging solutions. But the interposer also gives you the opportunity or potential to do more integration. For example, we can put a couple of die side by side on an interposer, as shown here, and connect those through the metal layers that are in that low-cost interposer technology. It's also possible to integrate some passive devices, filters or capacitors, into that interposer. Shown here is an example of some trench capacitors that could be etched into that silicon. So the interposer, while it's a very low-cost silicon technology, could offer opportunities to do a lot more integration. And finally, I'd like to touch on active TSV and the potential here for a lot more integration. Active TSV is where that through silicon via is integrated into the full CMOS process flow. So it allows you to pass the connections through the die without the use of any interposer or other type of packaging technology. So potentially you're able to stack multiple dies, different functions, perhaps very different technologies, in a very high performance, very low cost, very compact manner. So all of these innovative technologies, 3D FETs, SOI, and TSVs offer the potential for more SoC integration in the future. In conclusion, the integration levels in today's broadband communication SoCs are staggering, and this has been enabled through CMOS process scaling. Basically, the devices got better as we scale the technology. In addition, we need to employ smart design engineering to take advantage of those digital logic gates and use it to enhance our analog. And this brings with it opportunities for external devices using the non-mainstream CMOS processes. The examples we've shown are PoE, PMUs, and front ends for broadband tuners. Future SoCs will continue to use the advancements in CMOS technology, and while challenging, the 3D FETs and SOI devices and the innovative packaging technologies such as TSVs will offer additional opportunities for integration. Thank you for your attention.
Thank you very much for a wonderful lecture and overall SoC type of product line. 시간이 좀 있으니까 질문을 받도록 하겠습니다. 굉장히 프랙티컬한 강의를 해주셨는데 질문 있으시면 질문을 해주십시오. Yes, Lou?
So Neil, you talked about silicon tuners,
Right.
and you were saying that they've evolved from discrete solutions and now they're in fairly advanced CMOS process nodes. What kind of nodes are typically used for those silicon tuners? Where do you see that? Where do you see that now, or where do you see that heading?
We see continued scaling of those tuners into the advanced nodes as more functions are added, and the performance requirements get much higher for those tuners, driven by the bandwidth requirements.
Is this like 130 nanometer node, or is it 65, 45?
I think 65, 40, all of the advanced process nodes, you're seeing broadband tuner development.
Okay, thank you.
네, 있으시면 부탁드리겠습니다. Oh, yes.
I know you talked about 3D chips and whether that would be.
Do you believe that ultimately SoCs and analog will use 3D circuits, or do you think that it won't be, there will be too many challenges for that?
By, you mean 3D packaging technology? Or 3D?
No, I mean the FinFETs.
FinFETs, I think, are a reality. We've seen it already announced by Intel, for example, and that's a driver in our industry. So I expect the foundries will also continue to develop that, and it'll be a reality. But whether it makes sense for all of the applications, I think, is unclear, because it may be great for digital, for high performance applications. It's not clear if it's going to be good for analog, for SoCs. So I think it's a reality, but there may be some selected applications that will not use FinFETs.
예, 다른 그 질문은 영어, 한국어, 일본어로도 다 됩니다. 왜냐면 동시 통역이 지금 리얼하게 진행하기 리얼타임으로 진행되고 있기 때문에 언어에 조금 걱정이 되신다고 그러더라도 한국말로 질문하시면 되겠습니다. Lou, once again?
Yeah, Neil, maybe a touch on the last question. You know, one of the issues that you see with analog, particularly with scaling, is that it's very challenging with the reduced power supplies for them to be able to get the performance they want.
Is that me?
Do you see analog being able, are there partitioning issues where the analog can't go fast enough to keep up with the digital in terms of cranking out the next nodes as you look at on your chart?
Yeah, I think that's the key challenge, but how Broadcom has been able to address that is by the use of this DSP-assisted analog. So using those available and very inexpensive logic gates to compensate for those deficiencies in the analog performance. So I think we'll continue to do that. We'll continue to move to the advanced nodes and to take advantage of those logic gates to improve the analog performance.
예, 다른 질문 더 받겠습니다. 혹시 질문 있으세요? 네, 질문이 없으시면 수고해 주신 닐 키슬러 씨에게 다시 한번 박수를 부탁드리겠습니다. Thank you very much.